Welcome to this peaceful journey through the cosmos. Tonight, we'll explore the most amazing and calming facts about our universe. Find your most comfortable spot and let your body relax completely. Allow the day's stress to melt away as we drift together through the infinite beauty of space. Close your eyes if you wish, or keep them softly focused as we begin this gentle voyage among the stars. The universe holds more stars than grains of sand on every beach on Earth. When you look up at the night sky on a clear evening, you might see thousands of twinkling points of light. But this is just the tiniest fraction of what exists out there. Scientists have calculated that there are more stars in the observable universe than there are individual grains of sand on all the beaches and deserts of our entire planet combined. Each star is a massive ball of burning gas, some much smaller than our sun, others so large they could swallow our entire solar system. These stars come in different colors too. Some burn blue-white and extremely hot, while others glow red and cooler. Many of these distant suns have their own families of planets circling around them, just like our Earth circles our sun. This incredible number reminds us how vast and magnificent the cosmos truly is. As you breathe slowly and deeply, imagine floating peacefully among these countless stellar lights, each one a distant beacon in the cosmic ocean. The edge of what we can see stretches an amazing 93 billion light-years across. Our observable universe is like a giant bubble with Earth at the center, and we can only see as far as light has had time to travel since the very beginning of everything. This creates a boundary called the cosmic horizon, beyond which we simply cannot see, no matter how powerful our telescopes become. But here's something wonderful to think about. Beyond this edge, space likely continues on and on, filled with billions more galaxies, stars, and possibly other worlds with their own stories unfolding. The universe might even be infinite, stretching on forever without end. As you relax deeper into your comfortable position, picture yourself floating safely within this cosmic bubble, surrounded by the warm glow of distant galaxies, knowing that mystery and wonder extend far beyond what any eye has ever seen. Space itself is growing larger every single moment. The universe isn't just a container holding galaxies, it's more like a balloon being slowly inflated. As this cosmic balloon expands, it carries galaxies along with it, moving them farther apart from each other. The galaxies themselves aren't speeding through space like rockets. Instead, the space between them is stretching and growing, like dots drawn on a balloon that move apart as you blow it up. This gentle expansion has been happening for nearly 14 billion years, ever since the universe began. The amazing thing is that this stretching happens everywhere at once, between our galaxy and its neighbors, between distant clusters of stars, even in the space around you, though the effect is too small to notice in everyday life. As you settle more comfortably, imagine yourself floating peacefully in this slowly expanding cosmic ocean, carried gently along as space itself grows ever more vast and beautiful. The Big Bang wasn't actually an explosion in space, it was the birth of space and time themselves. Many people picture the beginning of the universe as a gigantic bomb going off somewhere in empty space. But the reality is far more mysterious and wonderful. Before the Big Bang, there was no space to explode into and no time to measure. In a single incredible instant, space and time themselves came into being, along with all the energy that would eventually become stars, planets, and even us. It's almost impossible for our minds to truly grasp this, but try to imagine that everything, every inch of space, every tick of time, every particle of matter all began from a single point, smaller than the period at the end of this sentence. From that tiny beginning, everything we know and love has grown and evolved over billions of years. As you breathe slowly and feel your body relaxing, think about how you were part of this amazing cosmic story that began so long ago. Ancient light from the universe's baby pictures still surrounds us everywhere. About 14 billion years ago, when the universe was very young and much smaller than it is today, it was filled with an incredibly hot, glowing fog. As space expanded and cooled down over hundreds of thousands of years, this fog gradually cleared, and for the first time, light could travel freely through the universe. That very same light is still all around us today, though it has been stretched and cooled by the expansion of space until it becomes invisible microwaves. Scientists can detect this ancient glow with special instruments, and it tells us amazing things about what the universe was like when it was just a baby. This faint radiation is like a cosmic background music, playing silently all around us, connecting us to the very dawn of time. As you rest peacefully, know that you are gently bathed in this primordial light that has been traveling through space since long before Earth, the Sun, or even our galaxy existed. Invisible matter forms a hidden skeleton that holds galaxies together. Most of the matter in the universe, about 85% of it, is completely invisible to us. We can't see it, touch it, or detect it directly in any way. Scientists call this mysterious substance dark matter, and even though we can't see it, we know it's there because of how it affects the things we can see. Without dark matter acting like an invisible glue, galaxies would fly apart and stars would drift away into the emptiness of space. This dark matter forms vast, invisible webs and highways throughout the universe, guiding where galaxies form and how they move. Think of it like an invisible scaffolding that holds up the beautiful cosmic architecture we can observe. Even though dark matter is mysterious and hidden, it plays the most important role in shaping the universe. As you sink deeper into relaxation, imagine this gentle, invisible presence supporting and connecting everything in the cosmos, including the very atoms that make up your relaxing body. A mysterious force is making the universe expand faster and faster. For many years, scientists expected that the expansion of the universe would gradually slow down over time, like a ball thrown into the air, eventually falling back down. But in one of the most surprising discoveries in all of science, they found that the universe's expansion is actually speeding up. Something is pushing everything apart with more and more force as time goes on. This mysterious energy makes up about 70% of everything in the universe, yet we have no idea what it is or how it works. Scientists call it dark energy, and it acts like an anti-gravity force, constantly pushing galaxies away from each other. This cosmic acceleration means that billions of years from now, the night sky will look very different, with many galaxies moved so far away that their light will no longer reach us. But for now, as you rest comfortably in this moment, the universe continues its ancient dance of expansion, carrying us gently through space and time. Galaxies live in a vast cosmic web of invisible highways. If you could see the entire universe from far away, it would look like an enormous spider web made of light and matter. Galaxies aren't scattered randomly through space like stars thrown across the sky. Instead, they line up along invisible threads and filaments made mostly of dark matter, creating a cosmic web that stretches across billions of light years. These galactic highways guide how galaxies move and grow, connecting distant parts of the universe in ways we're only beginning to understand. Between these bright filaments are enormous empty regions called voids, vast spaces where very few galaxies exist. The cosmic web shows us that even on the largest scales imaginable, the universe has a beautiful, organized structure. As your breathing becomes slower and more peaceful, picture yourself floating gently along one of these cosmic highways, passing by galaxies like distant cities of light connected by invisible roads of dark matter. Our Milky Way galaxy spins through space at incredible speed, carrying us on an amazing journey. Our home galaxy is like a giant cosmic carousel, spinning at over 500,000 miles per hour. Our entire solar system, including Earth, rides along with this galactic rotation, completing one full orbit around the galaxy's center every 250 million years. This means that since the dinosaurs lived on Earth, our solar system has traveled about halfway around the galaxy. Despite this incredible speed, the distances between stars are so vast that we never feel this cosmic motion, and collisions between stars are extremely rare. Our galactic neighborhood is a safe and stable place where planets can form and life can flourish. As you relax more deeply, imagine yourself as a cosmic traveler, riding peacefully through the galaxy on a journey that has been going on for billions of years and will continue for billions more. Sometimes galaxies meet and dance together in slow, beautiful cosmic ballets. Over the vast stretches of cosmic time, galaxies occasionally encounter each other and begin a graceful dance that can last for billions of years. When two galaxies come close together, their gravity slowly pulls them toward each other in spiraling orbits. Eventually, they merge into a single, larger galaxy, creating spectacular displays of star formation as their gas clouds collide and compress. These galactic mergers happen very slowly, so slowly that if you could watch one from beginning to end, you would need to live for billions of human lifetimes. Our own Milky Way galaxy is destined to dance with our neighbor, the Andromeda galaxy, in about 4 billion years. When this happens, the two galaxies will swirl together to create a new, larger galaxy. But don't worry, the stars are so far apart that our Sun and Earth will likely be completely safe during this cosmic dance. As you feel your body becoming more and more relaxed, imagine these galactic waltzes happening in slow motion across the universe. A cosmic choreography of unimaginable beauty and scale. Quasars shine as the brightest beacons in the distant universe, powered by hungry black holes. Far across the cosmos, in galaxies billions of light years away, some of the brightest objects in the universe are shining. These cosmic lighthouses are called quasars, and they can outshine entire galaxies containing hundreds of billions of stars. The incredible power of quasars comes from supermassive black holes at the centers of distant galaxies. As these black holes consume vast amounts of gas and dust, the material forms a swirling disk that heats up to millions of degrees and blazes with brilliant light. This light is so intense that we can see quasars across most of the observable universe, giving us glimpses of what galaxies were like when the universe was much younger. These distant beacons help scientists study the early universe and understand how black holes and galaxies grew together over cosmic time. As your mind grows quieter and more peaceful, think of these quasars as ancient cosmic lighthouses, sending their light across billions of years to reach us here and now. In the universe's earliest moments, space expanded faster than light in a process called inflation. Within the tiniest fraction of a second after the Big Bang, less time than it takes light to cross a distance smaller than an atom, the universe underwent an incredible transformation called cosmic inflation. During this brief moment, space itself expanded faster than the speed of light. growing from something smaller than a subatomic particle to something larger than a grapefruit in almost no time at all. This super-fast expansion smoothed out the universe and stretched tiny quantum ripples into the seeds that would eventually grow into galaxies and stars. Inflation explains many puzzling features of our universe, like why it looks so uniform in all directions, and why space appears to be geometrically flat. This remarkable process shows us that the universe's birth was even more dramatic and mysterious than we can easily imagine. As you continue to relax, let your mind drift back to that incredible first moment when everything began, when space and time themselves were born in a burst of cosmic inflation. The first stars ended the universe's dark age, lighting up the cosmos for the very first time. For hundreds of millions of years after the Big Bang, the universe was a cold, dark place with no stars to light the cosmic night. Gradually, gravity pulled together clouds of hydrogen and helium gas left over from the Big Bang, and these clouds grew denser and denser until they ignited as the first stars. These ancient stars were much more massive than most stars today, burning hot and bright but living relatively short lives. When they finally exploded as supernovas, they scattered heavier elements like carbon, oxygen, and iron into space, providing the raw materials that would eventually make planets and life possible. The light from these first stars also began to clear away the fog of hydrogen gas that filled the early universe, making space transparent for the first time. This cosmic dawn transformed the universe from a dark, empty void into the star-filled cosmos we know today. As your breathing becomes deeper and more regular, imagine the beauty of that first cosmic sunrise, when darkness gave way to light across the entire universe. High-energy particles race through space at nearly light speed, connecting us to violent cosmic events. Throughout the universe, some of the most powerful events imaginable, exploding stars, colliding black holes, and erupting galactic centers, fling tiny particles called cosmic rays across space at incredible speeds. These cosmic messengers travel at nearly the speed of light, crossing vast distances to reach Earth. When they arrive at our planet, they collide with atoms in our atmosphere, creating showers of secondary particles that rain down on us all the time. Most cosmic rays are harmless, but they create beautiful auroras when they interact with Earth's magnetic field near the poles. These energetic visitors connect us directly to the most dramatic events happening throughout the galaxy and beyond. Every second, billions of these cosmic ray particles pass through your body without you ever noticing, linking you to supernovas that exploded millions of years ago and black holes feeding in distant galaxies. As you settle more comfortably, think of these invisible cosmic messengers as gentle reminders that you are part of a vast, energetic, and interconnected universe. Our galaxy belongs to a massive supercluster containing thousands of neighboring galaxies. The Milky Way isn't alone in the cosmic darkness. Our galaxy is part of an enormous structure called the Laniakea supercluster, which contains thousands of galaxies, all bound together by gravity. This cosmic metropolis stretches across more than 500 million light-years and contains millions of billions of stars. The galaxies in our supercluster move together through space like a vast cosmic convoy, all influenced by the same gravitational currents and dark matter flows. Within Laniakea, galaxies interact with each other, sometimes merging or exchanging streams of gas and stars. Understanding our place within this vast galactic community helps us realize that even our entire galaxy is just one small part of an even grander cosmic structure. As you feel your body relaxing more and more, imagine floating peacefully within this enormous galactic neighborhood, surrounded by thousands of island universes, each containing billions of worlds and endless possibilities. Vast empty spaces called cosmic voids stretch between galaxy clusters like enormous cosmic bubbles. Between the bright filaments and clusters of galaxies lies something equally remarkable: enormous regions of nearly empty space called cosmic voids. These voids can be hundreds of millions of light years across, containing very few galaxies or stars. If you lived in the center of one of these voids, the night sky would appear almost completely dark, with only a few distant galaxy clusters visible as faint smudges on the horizon of space. These empty regions aren't truly empty. They contain sparse amounts of dark matter and gas. But compared to the dense galaxy clusters and filaments, they are remarkably vacant. The voids play an important role in shaping the cosmic web, acting like vast cosmic bubbles that push galaxies toward the filaments and clusters where they gather. As your mind becomes quieter and more peaceful, imagine the serene emptiness of these cosmic voids, vast spaces of tranquil darkness between the bright islands of galaxies. Nearly invisible neutrinos pass through everything, including your body, constantly. Right now, as you read these words, trillions of ghostly particles called neutrinos are streaming through your body, through the walls around you, and through the entire Earth without interacting with anything. These tiny messengers are created in the nuclear fires of stars, in exploding supernovas, and in the cosmic ray collisions happening in Earth's atmosphere. Neutrinos are so small and interact so weakly with matter that they can pass through entire planets as if they weren't there at all. Every second, about 100 billion neutrinos from the Sun alone pass through each square inch of your body. Scientists have to build enormous detectors deep underground or under thick ice to catch even a few of these elusive particles. Yet, despite being nearly invisible, neutrinos carry important information about the nuclear processes happening inside stars and the violent events occurring throughout the universe. As you continue to relax, think of these gentle cosmic visitors streaming through you right now, connecting you to the nuclear fires of distant stars and the energetic heart of our own sun. On the larger scales, the universe looks remarkably the same in every direction. When astronomers map the distribution of galaxies across vast distances, they discover something amazing. The universe looks essentially the same, no matter which direction they look. This cosmic uniformity, called isotropy, means there's no special direction or location in the universe. Whether you look toward the constellation Orion or toward the Southern Cross, the overall pattern of galaxy clusters, voids, and cosmic structure appears statistically identical. This uniformity extends to the cosmic microwave background radiation as well, which shows the same temperature and properties across the entire sky with only tiny variations. This remarkable smoothness tells us something profound about the universe's origin and evolution. It suggests that the laws of physics work the same way everywhere, and that our location in the cosmos isn't special or unique. As your breathing becomes even more peaceful and regular, rest in the knowledge that the universe's fundamental harmony and balance surrounds you on all sides. An ancient sea of neutrinos fills all of space, left over from the universe's first second. Within the first few moments after the Big Bang, when the universe was unimaginably hot and dense, it was flooded with neutrinos, tiny, nearly massless particles that barely interact with anything. As the universe expanded and cooled, these primordial neutrinos decoupled from other matter and began streaming freely through space. They've been traveling through the cosmos ever since, forming an invisible cosmic neutrino background that fills every corner of the universe. These relic neutrinos are incredibly difficult to detect because they rarely interact with matter, but they influence the evolution of cosmic structure in subtle ways. Detecting this cosmic neutrino background would give us an unprecedented view into the universe's first few seconds, when fundamental forces were separating and the basic structure of reality was taking shape. As you rest more deeply, imagine this ancient sea of neutrinos flowing gently around and through you, carrying with them the memory of the universe's fiery birth nearly 14 billion years ago. Scientists measure the universe's expansion with the Hubble constant, though it remains mysteriously difficult to pin down exactly. The universe has been expanding ever since the Big Bang, and astronomers have developed ways to measure exactly how fast this expansion is happening right now. This measurement is called the Hubble constant, and it tells us how quickly galaxies are moving away from us based on their distance. However, different methods of measuring the Hubble constant give slightly different results, creating what scientists call the Hubble tension. Some measurements suggest the universe is expanding a bit faster than others indicate. This discrepancy might point to new physics we don't yet understand, or it could reveal flaws in our current methods. Resolving this mystery is one of the most important challenges in modern cosmology, as the expansion rate affects our understanding of the universe's age, size, and ultimate fate. As your body settles into deeper relaxation, think of this cosmic mystery as a reminder that the universe still holds secrets waiting to be discovered. As galaxies move away from us, their light stretches to longer, redder wavelengths when you listen to a siren on an ambulance as it drives past. You notice that the sound becomes lower as the vehicle moves away from you. Something similar happens with light from distant galaxies. As these galaxies move away from us due to the expansion of space, their light gets stretched to longer wavelengths, making it appear redder than it actually is. This phenomenon, called redshift, is one of the key pieces of evidence that the universe is expanding. The more distant a galaxy is, the faster it's moving away from us, and the more its light is redshifted. By measuring this redshift, astronomers can determine both how far away a galaxy is and how long its light has been traveling to reach us. This means that when we look at distant galaxies, we're literally looking back in time, seeing them as they were billions of years ago. As you feel your body becoming more and more relaxed, imagine the light from distant galaxies stretching and cooling as it travels across space and time to reach your eyes. Astronomers use a clever step-by-step method called the cosmic distance ladder to measure vast cosmic distances. Measuring distances in space is like trying to figure out how far away a candle is when you can only see its tiny flame. Astronomers have developed an ingenious system called the cosmic distance ladder, where each rung of the ladder uses different techniques to measure farther and farther distances. They start with nearby stars whose distances can be measured using parallax, the slight shift in a star's apparent position as Earth orbits the Sun. Then they use these nearby stars to calibrate the brightness of special standard candle stars like Cepheid variables, whose true brightness is known. These standard candles can then be used to measure distances to nearby galaxies. Finally, even brighter standard candles like Type Ia supernovas can be used to measure distances to the most remote galaxies. Each step builds on the previous one, allowing us to map the scale of the entire observable universe. As your breathing becomes slower and deeper, appreciate this amazing human achievement that allows us to measure the immense cosmos using careful observation and clever reasoning. The cosmic horizon marks the farthest edge of what we can ever hope to see, because light travels at a finite speed and the universe has a finite age. there's a natural limit to how far we can see into space. This boundary, called the cosmic horizon, exists not because space ends there, but because light from beyond that distance simply hasn't had enough time to reach us yet. The cosmic horizon is constantly expanding as the universe gets older, gradually revealing more distant regions of space. However, due to the accelerating expansion of the universe, some regions that are currently beyond our horizon may remain forever out of reach. The cosmic horizon reminds us that our view of the universe, no matter how vast, is necessarily limited. There may be countless wonders beyond our sight, other galaxies, other solar systems, perhaps even other forms of life that we will never be able to observe. As you rest peacefully, contemplate the humbling beauty of this cosmic boundary that separates the known from the unknowable. Tiny grains of cosmic dust drift through space, playing a vital role in creating stars and planets. Space isn't empty. It's filled with microscopic dust grains made of elements like carbon, silicon, iron, and other materials forged in the nuclear furnaces of ancient stars. These cosmic dust particles are incredibly small, much finer than the dust in your home. But they play an enormous role in the universe's life cycle. When gas clouds in space begin to collapse under their own gravity to form new stars, cosmic dust helps cool these clouds by radiating away heat, allowing them to contract further. Around young stars, dust grains stick together to form larger and larger clumps, eventually building up into asteroids, planets, and moons. Cosmic dust also provides surfaces where complex molecules can form, including some of the organic compounds that are essential for life as we know it. As you sink deeper into relaxation, imagine these tiny cosmic gardeners working throughout space, helping to plant the seeds of new worlds and new possibilities. The universe's first stars were nearly pure hydrogen and helium, much simpler than stars today. The earliest stars in the universe, called population 3 stars, formed from clouds of gas that contained almost no heavy elements. These primordial gas clouds consisted of roughly 75% hydrogen and 25% helium, the only elements created in significant quantities during the Big Bang. These ancient stars were much more massive than most stars today, some containing hundreds of times more material than our Sun. They burned much hotter and brighter than modern stars, but lived relatively short lives before exploding as supernovas. When they exploded, they scattered the first heavy elements, carbon, oxygen, nitrogen, silicon, iron, and others, into space. These elements became the building blocks for the next generation of stars, which could form planets, and eventually, life itself. While none of these first-generation stars still exist today, their explosive deaths made possible everything we see in the universe now, including the elements that make up your own body. As your body continues to relax, remember that you are made of star stuff, created in the nuclear furnaces of ancient suns that lived and died billions of years ago. Many distant galaxies hide behind cosmic dust, glowing brightly in infrared light that our eyes cannot see. Throughout the universe, many galaxies are shrouded in thick clouds of cosmic dust that block visible light, making them nearly invisible to optical telescopes. However, this same dust absorbs energy from intense star formation happening within these galaxies and re-emits it as infrared radiation, heat, that we can detect with special space telescopes. When astronomers observe these dusty galaxies in infrared light, they reveal themselves as some of the most active star-forming regions in the universe. These hidden stellar nurseries help scientists understand how galaxies evolved over cosmic time and how the universe's star formation rate has changed over billions of years. Many of the atoms in your body were forged not just in stars, but in these intense periods of star formation happening in dusty, hidden galaxies throughout cosmic history. As you feel your body growing more peaceful and still, imagine these secret star factories working behind veils of cosmic dust, creating new suns and new worlds throughout the universe. Cosmic rays might subtly influence Earth's weather and climate. The high-energy particles called cosmic rays that constantly rain down on Earth from space may have a small but measurable effect on our planet's weather. When cosmic rays collide with molecules in Earth's atmosphere, they create ions, electrically charged particles that can act as seeds for cloud formation. Some scientists propose that changes in cosmic ray intensity caused by variations in solar activity or our galaxy's magnetic field might influence how many clouds form in Earth's atmosphere. Since clouds affect Earth's temperature by reflecting sunlight back to space, cosmic rays could potentially influence climate patterns over long time periods. While this effect is still being studied and debated, it represents a fascinating connection between the most energetic processes in the universe and the gentle rains and sunny days we experience on Earth. As your breathing becomes even more peaceful and regular, think about how Earth exists in constant communication with the cosmos, receiving these energetic messengers from the depths of space. The universe is dominated by regular matter, but the disappearance of antimatter remains one of science's greatest puzzles. According to our understanding of physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a burst of pure energy, leaving nothing behind. If the early universe contained equal amounts of both, everything should have been destroyed, leaving only energy and no atoms, no stars, no planets, and no us. Yet here we are, in a universe made almost entirely of matter, with antimatter extremely rare. This puzzle, called the baryon asymmetry problem, suggests that some unknown process in the early universe must have favored the survival of matter over antimatter. Understanding this imbalance is crucial to explaining why anything exists at all. Without this mysterious preference for matter, the universe would be a cold, empty void filled only with photons of light. As you rest more deeply, appreciate the miraculous fact that you exist at all in this matter-dominated universe, a living testament to one of cosmology's greatest unsolved mysteries. Gravity leaves subtle fingerprints on the ancient light we observe today. As light from the cosmic microwave background has traveled through space for nearly 14 billion years, it has passed near massive objects like galaxy clusters and black holes whose gravity has gently bent and distorted its path. These gravitational effects create tiny but measurable distortions in the cosmic background radiation that astronomers can detect with extremely sensitive instruments. By studying these subtle gravitational fingerprints, scientists can map the distribution of both visible matter and invisible dark matter throughout the universe. This technique, called gravitational lensing, has revealed the hidden architecture of the cosmos, showing us the invisible scaffolding of dark matter that holds galaxies and clusters together. These ancient photons carry with them a record of every massive object they've encountered on their journey across space and time. As your mind grows quieter and more peaceful, imagine these patient messengers of light, carrying their cargo of cosmic information across the vast expanses of space to reach us here and now. Light traveling through space gets gently warped and stretched by the gravity of massive objects. According to Einstein's theory of general relativity, Massive objects like galaxy clusters and black holes actually curve the fabric of space-time itself. When light travels near these massive objects, it follows the curved path of space-time, causing its trajectory to bend. This gravitational lensing can magnify and distort images of distant galaxies, sometimes creating beautiful arcs, rings, or multiple images of the same object. Nature has provided us with cosmic telescopes, massive galaxy clusters that focus light from even more distant galaxies behind them, allowing us to see objects that would otherwise be too faint to detect. Gravitational lensing also provides a unique way to study dark matter, which bends light through its gravity even though it's completely invisible. Through these cosmic funhouse mirrors, we can peer deeper into space and further back in time than would otherwise be possible. As you continue to relax, picture light taking gentle curved paths through the universe, guided by the invisible hand of gravity across billions of light years. The universe's first light began to shine when the earliest stars and galaxies formed. After hundreds of millions of years of cosmic darkness following the Big Bang, the universe finally lit up as the first stars ignited in the hearts of primordial galaxies. These pioneering stars, much more massive and brighter than most stars today, grouped together into the earliest galactic communities. Their collective brilliance pierced the cosmic darkness for the very first time, ending what astronomers call the cosmic dark ages. This ancient starlight marked a fundamental transformation in the universe's character, setting in motion the processes that would lead to the rich cosmic structures we observe today. The first galactic neighborhoods became the seeds from which our modern cosmic web of galaxy clusters and superclusters would eventually grow. As your body settles into deeper peace, imagine that momentous cosmic dawn when darkness gave way to light for the first time, and the universe began its transformation into the star-filled cosmos we call home. The universe became transparent when ultraviolet light ionized hydrogen gas throughout space. In the universe's youth, space was filled with neutral hydrogen atoms that absorbed most of the light trying to travel through it, making the cosmos opaque like a thick fog. The formation of the first stars and galaxies changed everything. These early stellar powerhouses emitted intense ultraviolet radiation that stripped electrons away from hydrogen atoms throughout space, turning the neutral gas into ionized plasma. This epoch of reionization cleared the cosmic fog that had filled the early universe, allowing light to travel freely across vast distances for the first time. This fundamental change opened windows throughout the cosmos, enabling the universe to become transparent and allowing us to observe distant galaxies billions of years later. Without this cosmic clearing of the fog, the universe would have remained dark and opaque, and we would never be able to see the beautiful tapestry of stars and galaxies that fills our night sky. As your breathing becomes deeper and more regular, think about this momentous transition when the universe literally cleared its throat and began to sing with light. Star formation reached its peak billions of years ago during cosmic high noon. Several billion years after the Big Bang, the universe experienced what astronomers call cosmic high noon, a period when star formation was happening at rates much higher than we observe today. During this golden age of stellar birth, galaxies throughout the universe were rapidly converting their gas reserves into new stars, enriching the cosmos with the heavier elements essential for planet formation and the development of life. This cosmic baby boom was fueled by abundant gas supplies and frequent galaxy mergers that triggered intense bursts of star formation. After this peak period, star formation rates gradually declined as galaxies consumed their gas reserves and evolved into the more mature stellar systems we see today. This ancient era of prolific stellar birth helped shape the chemical composition of the universe, creating and distributing the elements that would eventually form rocky planets like Earth. As you feel your muscles relaxing more completely, imagine this cosmic high noon when the universe was young and energetic, busily creating the stellar populations that light up our modern cosmos. Elements heavier than helium became more abundant as generations of stars lived and died. The early universe after the Big Bang contained mostly hydrogen and helium, with only trace amounts of heavier elements. But as the first stars formed and began their nuclear fusion processes, they started cooking up heavier elements in their cores: carbon, oxygen, nitrogen, silicon, iron, and many others. When these massive early stars reached the end of their lives and exploded as supernovas, they scattered these newly created elements into space, enriching the interstellar medium. Subsequent generations of stars formed from this enriched material, continuing the cosmic recycling process and creating even more complex elements. Over billions of years, this stellar alchemy gradually transformed the universe from a simple mixture of the lightest elements into the chemically rich environment we know today. The calcium in your bones, the iron in your blood, and the oxygen you breathe were all forged in the nuclear furnaces of ancient stars and distributed throughout space by stellar explosions. As you rest peacefully, remember that you are literally made of recycled stardust. Your body, a collection of atoms that have journeyed through space and time, from the cores of dying stars to become part of you. Giant filaments of dark matter connect galaxy clusters like a vast cosmic web. The largest structures in the universe are not individual galaxies, or even galaxy clusters, but enormous filaments of dark matter and gas that stretch across hundreds of millions of light years. These cosmic highways form a three-dimensional web throughout space, with galaxy clusters located at the intersections where multiple filaments meet. The filaments themselves are mostly composed of invisible dark matter, but they also contain streams of ordinary matter that flow along these dark matter scaffolds. Between the filaments lie enormous voids, vast regions of space that contain very few galaxies. This cosmic web structure influences how galaxies move and evolve over cosmic time, channeling matter along preferred directions and creating the large-scale architecture of the universe. Mapping these filaments helps scientists understand how matter is distributed on the largest scales and reveals the hidden skeleton that supports all the visible structures in the cosmos. As your body continues to relax, picture this invisible cosmic web surrounding you, connecting distant parts of the universe in an intricate network of dark matter highways and galactic intersections. Powerful jets of particles shoot out from supermassive black holes at the centers of galaxies. At the hearts of many galaxies lurk supermassive black holes containing millions or billions of times the mass of our Sun. When these cosmic giants actively feed on surrounding gas and dust, they don't just consume everything that comes near them. Instead, they launch tremendous jets of charged particles traveling at nearly the speed of light, extending for millions of light years into intergalactic space. These jets are among the most powerful phenomena in the universe, carrying enormous amounts of energy far from their source. By heating and pushing away material in their host galaxies, these black hole jets regulate star formation and influence galactic evolution over cosmic time. The interaction between supermassive black holes and their host galaxies represents one of the most important feedback mechanisms shaping the universe's structure. These cosmic fire hoses demonstrate that black holes aren't just consumers of matter. They're also powerful engines that can affect their entire galactic neighborhoods. As your mind grows quieter and more peaceful, imagine these cosmic jets as gentle streams of energy flowing through the universe, connecting black holes to their galactic communities across vast distances. Massive galaxy clusters form the densest gathering places in the cosmic web. Galaxy clusters are the universe's largest gravitationally bound structures, containing hundreds or even thousands of individual galaxies packed into regions millions of light-years across. These cosmic metropolises represent the densest nodes in the vast network of dark matter filaments that spans the universe. Within galaxy clusters, individual galaxies move at tremendous speeds, held together by the immense gravitational pull of dark matter and hot gas. The space between cluster galaxies is filled with extremely hot gas that glows in X-ray light, creating some of the most energetic environments in the cosmos. Galaxy clusters act like cosmic laboratories where astronomers can study how galaxies interact, merge, and evolve under extreme gravitational conditions. As you feel your body sinking deeper into relaxation, imagine these cosmic cities of galaxies, vast communities of stellar islands bound together by invisible forces across unimaginable distances. The universe's shape is incredibly close to being perfectly flat, not curved like a sphere or saddle. One of the most remarkable discoveries about our universe is that its overall geometry is almost perfectly flat on the largest scales. This means that if you could draw two parallel lines across the entire observable universe, they would stay parallel forever, never converging or diverging. This flatness is actually quite surprising and requires an incredibly precise balance between the universe's total energy content and its expansion rate. In a curved universe, parallel lines would eventually meet like longitude lines on Earth, or diverge like lines drawn on a saddle. The flatness of space affects how light travels across cosmic distances and influences the ultimate fate of the universe, suggesting it will expand forever rather than eventually collapsing back on itself. This geometric perfection supports theories about cosmic inflation and reveals deep connections between the universe's past and future. As your breathing becomes slower and more peaceful, rest in the knowledge that you exist within a cosmos of remarkable mathematical harmony and balance. Tiny temperature differences in the ancient cosmic background light seeded all the structures we see today. When we observe the cosmic microwave background radiation, that ancient afterglow of the Big Bang, it appears almost perfectly uniform in temperature across the entire sky. But when scientists look very carefully with extremely sensitive instruments, they find tiny variations in temperature, differences of only a few millionths of a degree. These minuscule ripples in the cosmic background represent slight differences in density that existed in the very early universe. Over billions of years, gravity has amplified these tiny variations, causing matter to clump together in the slightly denser regions while leaving the less dense areas relatively empty. These ancient temperature fluctuations are literally the seeds from which all cosmic structures grew. Galaxies, galaxy clusters, and the entire cosmic web trace their origins back to these primordial ripples. Without these tiny variations, the universe would have remained perfectly smooth and empty, with no stars, no planets, and no life. As you continue to relax, marvel at how the grandest structures in the cosmos grew from variations so small they're almost impossible to detect. Scientists face a fundamental limitation called cosmic variance because we can observe only one universe. Imagine trying to understand the rules of a card game by watching only a single hand being played. This is similar to the challenge cosmologists face when studying the universe. Since we have access to only one cosmic realization, our own universe, we cannot be certain whether the patterns and structures we observe are universal laws or just cosmic accidents. When scientists measure things like the distribution of galaxies or fluctuations in the cosmic background radiation, their measurements carry inherent uncertainties because we don't have other universes to compare with. Some features we observe might be typical of all possible universes, while others might be unique quirks of our particular cosmic neighborhood. This limitation, called cosmic variance, challenges researchers to develop sophisticated statistical methods and theoretical models to separate universal truths from cosmic coincidences. As your body grows more peaceful and still, contemplate the remarkable fact that all of human knowledge about the cosmos comes from studying this single, precious example of a universe that we call home. Scientists estimate cosmic history by measuring the ages of distant galaxies and looking back in time. Because light travels at a finite speed, when astronomers observe distant galaxies, they're literally looking back in time to see these stellar systems as they existed billions of years ago. By analyzing the light from galaxies at different distances, scientists can determine when these galaxies formed their stars and estimate their ages. The most distant galaxies visible today appear to us as they were when the universe was very young, giving us snapshots of cosmic history across many different epochs. By combining age estimates from galaxies at various distances with other observations, astronomers have assembled a detailed timeline of how the universe has evolved from its earliest moments to the present day. This cosmic archaeology reveals how star formation rates have changed over time, how galaxies have grown and merged, and how the chemical composition of the universe has evolved as successive generations of stars have lived and died. As your mind grows quieter and more peaceful, think of astronomers as cosmic historians, reading the story of the universe written in the ancient light of distant stars. Hypothetical cosmic strings might be ultra-thin relics from the universe's earliest moments. Some theories about the very early universe predict the existence of cosmic strings, incredibly thin, almost one-dimensional defects in the fabric of space-time itself. If they exist, these cosmic strings would be thinner than a proton but could stretch across the entire observable universe, containing enormous amounts of energy packed into virtually no volume. Cosmic strings might have formed during phase transitions in the first fraction of a second after the Big Bang, when the fundamental forces of nature were separating from each other. These hypothetical objects could produce detectable gravitational waves as they vibrate and interact, or create subtle distortions in the cosmic microwave background radiation. While no direct evidence for cosmic strings has been found yet, their discovery would provide unprecedented insights into the physics of the very early universe and the fundamental structure of reality itself. As you rest more deeply, imagine these invisible threads that might weave through the cosmos, connecting the smallest scales of physics to the largest structures in space. High-energy X-rays shine from distant black holes as they devour surrounding matter. Deep within the centers of many galaxies lie supermassive black holes that can contain millions or billions of times the mass of our Sun. When these cosmic giants actively consume gas and dust from their surroundings, the material doesn't simply disappear quietly. Instead, it forms a swirling accretion disk that heats up to millions of degrees due to friction and the intense gravitational forces involved. This superheated material glows brilliantly in X-ray light, creating some of the most energetic and luminous objects in the universe. These X-ray emissions can outshine entire galaxies and be detected by space telescopes across billions of light years. The high-energy radiation from feeding black holes provides astronomers with a way to study these mysterious objects and understand how they grow and influence their host galaxies over cosmic time. As you feel your body relaxing more completely, picture these cosmic beacons shining across the universe, their X-ray glow carrying information about some of the most extreme environments that exist anywhere in nature. Turbulent gas clouds within galaxies create the birthplaces where new stars are born. Within every galaxy, vast clouds of gas and dust drift through space in a state of constant, chaotic motion. These interstellar clouds are stirred by multiple forces: gravity pulling material together, shock waves from exploding stars pushing it apart, magnetic fields threading through the gas, and stellar winds from massive stars. This cosmic turbulence creates a complex dance of compression and expansion within the clouds. When turbulence compresses part of a cloud enough, gravity can take over and cause that region to collapse, heating up until nuclear fusion ignites and a new star is born. The balance between turbulent motion and gravitational collapse determines how quickly galaxies can form new stars and how massive those stars become. Understanding this delicate interplay helps astronomers explain why some galaxies are prolific star factories while others have slowed their star formation to a trickle. As your breathing becomes even more regular and peaceful, imagine these cosmic nurseries where turbulent gas slowly settles into the bright points of light we see as stars. Pulsars and distant galaxies fill space with radio waves that create an invisible cosmic symphony. Throughout the universe, many different types of objects emit radio waves, a form of light that our eyes cannot see, but radio telescopes can detect. Pulsars, which are rapidly spinning neutron stars left behind after massive stellar explosions, sweep beams of radio waves through space like cosmic lighthouses. Many galaxies also emit radio waves from energetic processes like star formation, supernova explosions, and jets from their central black holes. This creates a constant background of radio noise filling all of space, like a cosmic radio station playing throughout the universe. Radio astronomy allows scientists to study objects and processes that are often invisible in optical light, revealing hidden aspects of stellar death, galactic evolution, and high-energy astrophysics. The radio universe looks completely different from the optical universe we see with our eyes, populated by exotic objects and energetic phenomena that would otherwise remain hidden. As you sink deeper into relaxation, imagine tuning in to this invisible cosmic radio symphony playing all around us, carrying messages from some of the most exotic objects in the universe. Exploding stars launch cosmic ray particles that speed through space for millions of years. When massive stars reach the end of their lives and explode as supernovas, they create some of the most violent events in the universe. These stellar explosions generate tremendous shock waves that can accelerate particles, mostly protons and atomic nuclei too, nearly the speed of light. These cosmic ray particles then journey through the galaxy for millions of years, bouncing off magnetic fields and traveling vast distances before eventually reaching Earth. When cosmic rays collide with our planet's atmosphere, they create cascades of secondary particles that rain down on the surface, connecting us directly to ancient stellar explosions that happened long before Earth even existed. Cosmic rays influence the chemistry of interstellar space and may even affect Earth's climate in subtle ways. They serve as high-energy messengers from some of the universe's most dramatic events, carrying energy and information across the galaxy. As you continue to rest peacefully, Think of these energetic particles as cosmic mail carriers, delivering messages from stellar explosions that occurred millions of years ago in distant parts of our galaxy. Patterns in the polarization of ancient light reveal secrets about the universe's birth. The cosmic microwave background radiation doesn't just shine with a uniform glow. Careful measurements reveal that this ancient light is also polarized, meaning the light waves oscillate preferentially in certain directions rather than randomly. This subtle polarization carries encoded information about gravitational waves and density fluctuations that existed in the very first moments after the Big Bang. By studying these delicate polarization patterns, scientists can test theories about cosmic inflation and learn about quantum fluctuations that were stretched to cosmic scales during the universe's rapid early expansion. The polarization of the cosmic microwave background provides one of our most direct connections to the physics of the universe's birth, offering clues about forces and processes that operated under conditions impossible to recreate in any laboratory. These measurements require incredibly sensitive instruments and careful analysis to separate the cosmic signal from local interference. As your body settles into deeper peace, appreciate the remarkable fact that we can decode messages about the universe's first moments by studying the subtle properties of ancient light that has traveled across space and time to reach us. Ultraviolet radiation from early stars cleared the cosmic fog and made the universe transparent. After the cosmic microwave background was released about 380,000 years after the Big Bang, the universe entered a period sometimes called the Cosmic Dark Ages, when space was filled with neutral hydrogen gas that absorbed most ultraviolet light. This made the universe opaque to short-wavelength radiation, like trying to see through a thick fog. When the first stars finally formed hundreds of millions of years later, they emitted intense ultraviolet light that began ionizing the hydrogen gas throughout space. This process, called reionization, stripped electrons away from hydrogen atoms and transformed the neutral gas into a transparent ionized plasma. The reionization epoch fundamentally changed the universe's character, clearing the cosmic fog and allowing ultraviolet light to travel freely across vast distances for the first time since the early moments after the Big Bang. This transformation opened new windows on the cosmos and enabled the universe to become the transparent, light-filled space we observe today. As your mind grows quieter, picture this cosmic clearing of the fog when starlight first began to shine freely across the universe. The first galaxies were the cosmic pioneers that lit up and transformed the early universe. As gravity slowly assembled the first significant collections of stars from primordial gas clouds, these early galactic communities became the sources of the intense ultraviolet radiation that ionized hydrogen throughout space. The first galaxies were likely smaller and more irregular than the grand spiral and elliptical galaxies we see today, but they played a crucial role in the universe's evolution. These galactic pioneers not only provided the energy needed to clear the cosmic fog during reionization, but also began the process of enriching space with heavy elements created by stellar nucleosynthesis. The formation and evolution of the first galaxies set the stage for all subsequent cosmic structure formation, establishing the foundation upon which our modern universe of galaxy clusters and superclusters would eventually build. As your breathing becomes deeper and more peaceful, think of these early galactic communities as cosmic lighting the way for all the stellar systems that would follow. Dark energy's mysterious repulsive force continues to accelerate the universe's expansion, despite gravity's tendency to pull everything together. Observations have revealed that the universe's expansion is actually speeding up over time. This cosmic acceleration is driven by dark energy, a mysterious form of energy that makes up about 70% of the universe's total content. Unlike matter and radiation, dark energy appears to have a repulsive gravitational effect, pushing space itself to expand faster and faster. The nature of dark energy remains one of the deepest mysteries in modern physics. We don't know what it is, where it comes from, or how it works. This cosmic acceleration means that galaxies are moving away from each other at ever-increasing rates. And billions of years from now, distant galaxies will have moved so far away that their light will no longer be able to reach us. Understanding dark energy is crucial for predicting the ultimate fate of the universe and our place within it. As you relax more deeply, contemplate this invisible force that shapes the destiny of everything in existence, gently but inexorably pushing the cosmos toward an ever more expanded future. Scientists use something called the scale factor to describe how distances change as the universe expands. Cosmologists have developed a mathematical way to track the universe's expansion over time using a quantity called the scale factor. This dimensionless number describes how the relative distances between galaxies change as space itself stretches. When the scale factor doubles, the distance between any two galaxies also roughly doubles, illustrating how cosmic expansion affects the entire universe uniformly. By measuring how the scale factor has changed over cosmic history, scientists can understand the expansion rate at different epochs and how forces like matter, radiation, and dark energy have influenced cosmic evolution. The scale factor provides a simple but powerful way to describe the vast, ongoing transformation of the universe from its dense, compact beginning to its current expanded state. This mathematical tool helps cosmologists chart the universe's past and predict its future evolution. As you feel your body becoming more and more relaxed, imagine this cosmic scale factor as a gentle cosmic heartbeat, marking the rhythm of the universe's growth across billions of years. The universe's overall curvature affects light paths and cosmic geometry on the largest scales. Just as Earth's surface is curved even though it appears flat to us locally, the universe as a whole might have an overall curvature that affects how light travels across cosmic distances and how geometric relationships work on the largest scales. Current observations suggest the universe is remarkably close to being geometrically flat, meaning that parallel light rays stay parallel even across billions of light years. In a positively curved universe, like the surface of a sphere, parallel lines would eventually converge, while in a negatively curved universe, like a saddle shape, they would diverge. The universe's curvature is intimately related to its density and expansion rate, and it determines whether the cosmos will expand forever or eventually reach. The fact that our universe appears to be so close to perfectly flat is actually quite remarkable and provides important clues about cosmic inflation and the fundamental properties of space and time. As your mind grows more peaceful, rest in the geometric harmony of our flat universe, where the familiar rules of geometry extend across the vastest scales imaginable. Matter distributes evenly across the universe when viewed on the largest scales. When astronomers map the distribution of galaxies and dark matter across hundreds of millions of light years, they find that the universe is remarkably homogeneous on these vast scales, while galaxies cluster together locally and large voids exist between them. The overall density of matter averages out to be essentially the same everywhere, when viewed across sufficiently large volumes of space. This large-scale homogeneity means that no region of the universe is fundamentally different from any other. There are no special places or preferred directions on cosmic scales. This uniformity simplifies our mathematical models of cosmic evolution and supports the cosmological principle, which assumes that the universe looks the same to observers anywhere within it. The homogeneous distribution of matter provides crucial evidence for our understanding of cosmic inflation and the processes that shaped the early universe. As you continue to relax, appreciate this cosmic democracy where every region of space is, on average, equivalent to every other region across the grandest scales of existence. The universe appears essentially the same in every direction we look. This property, called cosmic isotropy, means that when we observe the universe from Earth, it looks statistically identical no matter which direction we point our telescopes. The cosmic microwave background shows the same temperature and properties across the entire sky, with only tiny variations that seed cosmic structure. Galaxy surveys reveal the same statistical patterns of clustering and void formation in all directions. This isotropy, combined with homogeneity, forms the foundation of the cosmological principle and allows scientists to develop universal models that describe cosmic evolution everywhere. The remarkable uniformity of the universe in all directions suggests that the fundamental laws of physics and the initial conditions that gave rise to cosmic structure are the same throughout space. This cosmic democracy extends our local physical laws to the entire observable universe. As your breathing becomes slower and more regular, feel yourself at the center of this isotropic cosmos, equally connected to the wonders that surround us in every direction across the vast expanse of space. The discovery of cosmic microwave background radiation provided crucial evidence for the Big Bang theory. In 1965, two scientists named Arno Penzias and Robert Wilson were trying to eliminate mysterious noise from their radio antenna when they accidentally discovered something extraordinary, a faint, uniform microwave signal coming from every direction in the sky. This cosmic microwave background radiation turned out to be the cooled remnant of the hot, dense state that existed in the early universe, exactly as predicted by Big Bang theory. The discovery transformed cosmology from a field based largely on speculation into a precision science supported by observational evidence. Detailed measurements of this ancient radiation have since revealed tiny temperature fluctuations that represent the seeds from which all cosmic structures grew. The cosmic microwave background serves as our oldest baby picture of the universe, showing us what conditions were like when the cosmos first became transparent to light. As you rest peacefully, think of this ancient glow that still surrounds us, carrying information from the universe's infancy across nearly 14 billion years of space and time. Cosmic history unfolds across an enormous range of timescales, from fractions of seconds to billions of years. The story of the universe begins in the Planck epoch, just a tiny fraction of a second after the Big Bang, when the fundamental forces of nature were unified and the laws of physics as we know them may not have applied. From these first moments, cosmic history unfolds through distinct epochs: inflation, nucleosynthesis, recombination, the cosmic dark ages, reionization, and galaxy formation. Each phase brought profound changes to the universe's structure and composition. The entire timeline reveals a cosmos in constant evolution, where every moment connects the past to the future in an ongoing cosmic narrative. Billions of years passed as galaxies formed and evolved. Stars lived and died, and the heavy elements necessary for planets and life were created and distributed throughout space. Understanding this vast timeline helps us appreciate our place in the cosmic story and the deep connections between past, present, and future. As you feel your body growing more peaceful, contemplate your own place in this grand cosmic timeline. A brief but meaningful moment in the universe's long journey. The observable universe slowly grows larger as light from more distant regions reaches us. The boundary of the observable universe is determined by the cosmic light horizon, the maximum distance from which light has had time to reach us since the Big Bang. As time passes, this horizon gradually expands, allowing us to see slightly more distant galaxies and cosmic structures. However, because the universe is expanding, some regions that are currently beyond our observational reach may remain forever hidden from view. The expansion of the observable universe represents the gradual unveiling of cosmic history, as light from increasingly distant and ancient sources finally completes its long journey to Earth. This expanding horizon reminds us that our view of the cosmos, however vast it may seem, is necessarily limited by the finite age of the universe and the finite speed of light. Each passing year reveals new depths of space and time, gradually expanding our cosmic perspective. As you sink deeper into relaxation, imagine this slowly expanding sphere of visibility, gradually revealing new cosmic vistas and ancient secrets from the depths of space and time. Brief but incredibly powerful gamma-ray bursts briefly outshine entire galaxies. Among the most energetic events in the universe are gamma-ray bursts, intense flashes of high-energy radiation that can last from milliseconds to several minutes. These cosmic explosions release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. Most gamma-ray bursts are thought to result from the collapse of massive stars into black holes or from collisions between neutron stars. Despite their brief duration, these events can be detected across most of the observable universe, serving as cosmic beacons that illuminate the distant cosmos. Gamma-ray bursts provide unique laboratories for studying extreme physics under conditions that cannot be replicated on Earth. They also serve as probes of the early universe, since the most distant bursts we observe show us what conditions were like when the cosmos was much younger. As you continue to rest peacefully, think of these brief cosmic fireworks, brilliant flashes of energy that briefly illuminate dark corners of the universe with their intense but fleeting light. The expansion of space stretches light waves, creating the redshift that reveals cosmic distances. As the universe expands, it doesn't just carry galaxies farther apart, it also stretches the light waves traveling through space. This stretching increases the wavelength of light, shifting it toward the red end of the electromagnetic spectrum in a phenomenon called cosmological redshift. The amount of redshift in a galaxy's light tells us both how far away it is and how fast it's receding from us due to cosmic expansion. This effect allows astronomers to use distant galaxies as cosmic mile markers, mapping the expansion rate of the universe across different epochs. Redshift also enables us to look back in time, since light from highly redshifted galaxies left them billions of years ago when the universe was much younger and denser. This cosmic time machine effect allows us to study galaxy evolution and cosmic history directly. As your body settles into deeper peace, imagine these light waves gently stretching as they travel across expanding space, carrying messages from distant worlds and ancient times. Ancient relic neutrinos have been streaming through space since the universe was only 1 second old. In the first few moments after the Big Bang, When the universe was unimaginably hot and dense, it was filled with neutrinos, tiny, nearly massless particles that barely interact with anything else. Within the first second of cosmic history, these neutrinos decoupled from the hot plasma that filled the early universe and began streaming freely through space. They have been traveling virtually unimpeded ever since, forming what scientists call the cosmic neutrino background. These relic neutrinos are even more ancient than the photons of the cosmic microwave background, carrying information about conditions in the universe's very first moments, though incredibly difficult to detect due to their weak interactions with matter. These primordial neutrinos influenced the formation of cosmic structures and continue to provide clues about fundamental physics and the universe's earliest epochs. As your breathing becomes more peaceful, think of these ghostly messengers from the universe's first, second, still journeying through space after nearly 14 billion years, connecting us to the cosmos's fiery birth. Cosmic voids are vast desert regions between galaxy clusters where very little exists. Scattered throughout the cosmic web are enormous regions called voids, volumes of space that can stretch across hundreds of millions of light years, but contain very few galaxies or visible matter. These cosmic deserts represent some of the emptiest places in the universe, with matter densities far below the cosmic average. Though nearly empty, voids play crucial roles in shaping cosmic evolution by influencing the gravitational flows that guide galaxy formation and movement. The contrast between dense galaxy clusters and nearly empty voids creates the foam-like structure of the cosmic web. Studying voids helps scientists understand dark energy, dark matter, and the large-scale forces that govern cosmic architecture. These silent expanses remind us that most of the universe's volume consists of nearly empty space, punctuated by islands of matter and light. As you feel your muscles relaxing completely, imagine floating peacefully through one of these cosmic voids, surrounded by the profound quiet of nearly empty space, with only distant galaxy clusters glowing like cities on the far horizon. Galaxies grow larger and more complex through slow mergers that unfold over billions of years. The galaxies we see today are not the same as they were billions of years ago. These stellar cities are dynamic systems that grow and evolve through interactions with their neighbors. When galaxies encounter each other, they begin gravitational dances that can last for billions of years before finally merging into single, larger systems. These cosmic collisions often trigger bursts of star formation as gas clouds collide and compress, creating spectacular stellar fireworks. Galaxy mergers can also feed the supermassive black holes at galactic centers and reshape the orbits of billions of stars. Our own Milky Way galaxy has grown through many such mergers over cosmic time and will eventually merge with the nearby Andromeda galaxy in several billion years. This process of hierarchical growth built up the massive elliptical galaxies we observe today from smaller building blocks. As you rest more deeply, picture these slow cosmic dances, where entire galaxies waltz together across billions of years, creating ever grander stellar communities through their patient gravitational embrace. Invisible magnetic fields thread through galaxies, guiding cosmic rays and shaping star formation. Though we cannot see them directly, magnetic fields permeate galaxies, threading through interstellar space and influencing the behavior of charged particles and ionized gas. These galactic magnetic fields are much weaker than Earth's magnetic field, but they extend across thousands of light years and play important roles in galactic evolution. They help channel the flow of cosmic rays through the galaxy, influence the collapse of gas clouds where stars form, and affect how matter falls into central black holes. Galactic magnetic fields also interact with stellar winds and supernova shockwaves, creating complex patterns of matter flow throughout stellar systems. Though invisible, these magnetic forces add another layer of complexity to the cosmic web, weaving unseen influences through the visible structures of stars and gas. As your mind grows quieter and more peaceful, imagine these invisible magnetic threads connecting distant parts of galaxies, creating hidden highways for cosmic rays and subtle influences on stellar birth and death. Cosmic rays occasionally cause mutations in DNA, connecting Earth's biology to cosmic events. The high-energy particles, called cosmic rays, that constantly bombard Earth from space carry enough energy to penetrate living organisms and occasionally damage DNA molecules. Most of this damage is repaired by cellular mechanisms or causes no lasting effects. But some cosmic ray hits contribute to the natural mutation rate that drives biological evolution. This means that cosmic events like distant supernova explosions have played a subtle but ongoing role in shaping life on Earth over geological time. The connection between cosmic rays and genetic mutations links our planet's biological history to the energetic processes unfolding throughout the galaxy. Even more dramatically, some scientists have proposed that nearby supernova explosions might have influenced major evolutionary transitions or mass extinction events in Earth's past. As you continue to relax, appreciate this deep connection between life on Earth and the cosmic environment, where particles from stellar explosions billions of miles away occasionally interact with the very molecules that make you who you are. Bubble-like structures might have formed during phase transitions in the very early universe. In the universe's first moments, as it expanded and cooled, the fundamental forces of nature underwent dramatic changes called phase transitions, similar to how water changes from steam to liquid to ice as it cools. Some theories suggest these cosmic phase transitions might have created bubble-like structures in the fabric of space-time itself. These bubbles would have expanded and collided with each other, potentially leaving detectable imprints on the cosmic microwave background or producing gravitational waves that we might someday observe. Such phase transition bubbles could provide crucial insights into the physics of the early universe and the processes that separated the fundamental forces. While these structures remain hypothetical, their possible detection would open unprecedented windows into the universe's first moments and the deepest levels of physical reality. As you feel your body settling into complete relaxation, imagine the early universe as a cosmic bubble bath, with reality itself going through dramatic transformations in those first crucial moments after the Big Bang. Tiny fluctuations in the ancient cosmic background light reveal the universe's initial conditions. When we study the cosmic microwave background radiation with extremely sensitive instruments, we can detect temperature variations of only a few millionths of a degree across the sky. These incredibly subtle fluctuations represent density variations that existed in the early universe when this ancient light was first released. Over billions of years, gravity has amplified these tiny differences into the rich cosmic structures we observe today. Galaxies, clusters, and the cosmic web all trace their origins back to these primordial ripples. The precise pattern of these fluctuations provides crucial information about the fundamental parameters of the universe, including its age, composition, and geometry. By studying these delicate imprints from the cosmic past, scientists can test theories about inflation, dark matter, and the processes that shaped our universe. As your breathing becomes slower and deeper, marvel at how the grandest structures in the cosmos grew from variations so small they require the most sensitive instruments ever built to detect. Cosmic rays help create the beautiful northern and southern lights that dance across polar skies. When high-energy cosmic ray particles from deep space interact with Earth's magnetic field and atmosphere, they contribute to one of nature's most spectacular displays, the aurora borealis and aurora australis. These cosmic visitors, along with particles from solar wind, strike gas molecules in the upper atmosphere and cause them to emit light in brilliant curtains of green, red, blue, and purple. The auroras represent a visible connection between Earth and the high-energy processes happening throughout the cosmos. Every time you see the northern or southern lights dancing across the sky, you're witnessing the interaction between our planet and cosmic rays that may have originated in supernova explosions or other violent events thousands of light years away. This cosmic light show reminds us that Earth exists within a dynamic galactic environment where energetic particles from distant stellar explosions regularly interact with our world. As you rest peacefully, imagine these cosmic rays painting their ethereal artwork across polar skies, creating beauty from the collision between space and atmosphere. Galaxies flow along invisible gravitational currents shaped by dark matter's distribution. The movement of galaxies through space isn't random. They follow gravitational currents and flows determined by the large-scale distribution of matter, especially invisible dark matter. These cosmic rivers guide galaxies along preferred paths through the universe, channeling them toward dense clusters and away from nearly empty voids. Understanding these gravitational flows helps astronomers map the invisible scaffolding of dark matter that underlies all visible cosmic structure. The motion of our own local group of galaxies, including the Milky Way and Andromeda, is influenced by these large-scale flows as we're gradually pulled toward the massive Virgo cluster and other distant concentrations of matter. This cosmic choreography shows us that even galaxies are part of larger patterns of motion and structure that extend across hundreds of millions of light years. As you feel your body becoming completely relaxed, picture these invisible currents flowing through space, gently guiding galaxies along cosmic highways defined by the distribution of matter and energy. The last scattering of photons occurred about 380,000 years after the Big Bang. There was a crucial moment in cosmic history when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this epoch, called recombination, the universe was filled with free electrons that constantly scattered photons, making space opaque to light. When recombination occurred about 380,000 years after the Big Bang, photons could finally travel freely through space without being absorbed or scattered. This moment of last scattering released the cosmic microwave, background radiation that we observe today, the oldest light in the universe. From that moment forward, space became transparent, allowing light to journey across cosmic distances and eventually enabling us to see stars, galaxies, and the cosmic web. This transformation from an opaque to transparent universe was one of the most important transitions in cosmic history. As your mind grows more peaceful, contemplate this cosmic moment of clearing, when the universe first became transparent and light began its long journey across space and time. Small temperature variations in ancient light provided the gravitational seeds for all cosmic structures. The cosmic microwave background radiation appears almost perfectly uniform, but incredibly precise measurements reveal tiny temperature differences, variations of only a few millionths of a degree, scattered across the sky. These minuscule fluctuations correspond to slight density differences in the matter that filled the early universe. In regions that were slightly denser than average, gravity was a little stronger and began pulling in more matter from the surroundings. Over hundreds of millions and billions of years, these small density enhancements grew under their own gravity, eventually becoming the galaxies, galaxy clusters, and cosmic web filaments we observe today. Without these tiny primordial seeds, the universe would have remained perfectly smooth and empty forever. The entire rich tapestry of cosmic structure traces its origins back to these barely detectable variations in the universe's baby picture. As you continue to rest, appreciate how the grandest structures in the cosmos grew from seeds so small that detecting them requires the most sensitive instruments humanity has ever built. Gravitational tides from neighboring galaxies slowly stretch and reshape stellar systems over cosmic time, just as the moon's gravity creates tides in Earth's oceans. The gravitational fields of nearby galaxies create tidal forces that can stretch and distort more distant stellar systems. These galactic tides are incredibly weak compared to oceanic tides, but over the vast timescales of cosmic evolution, they can significantly alter galaxy shapes and trigger episodes of star formation. Tidal interactions between galaxies can pull out streams of stars and gas, create spectacular tidal tails stretching across hundreds of thousands of light years, and eventually lead to galactic mergers. Our own Milky Way galaxy experiences tidal forces from nearby galaxies and exerts its own tidal influence on smaller satellite galaxies like the Magellanic Clouds. These gentle but persistent gravitational tugs remind us that galaxies don't exist in isolation, but are constantly influenced by their cosmic neighbors. As you feel your body growing more and more relaxed, imagine these subtle tidal forces working across cosmic time, slowly sculpting the shapes of galaxies through their patient gravitational embrace. Quantum fluctuations during cosmic inflation grew into the largest structures in the universe. During the brief period of cosmic inflation that occurred in the universe's first fraction of a second, tiny quantum fluctuations, random variations in energy that exist at the smallest scales of reality, were rapidly stretched to enormous sizes. These quantum ripples, which would normally exist only at subatomic scales, were inflated to cosmic proportions and became the seeds from which all large-scale structures would eventually grow. Over billions of years, gravity amplified these quantum origins into galaxies, galaxy clusters, and the cosmic web that spans the observable universe. This remarkable process links the quantum world of atomic physics to the grandest structures in the cosmos, showing how the smallest and largest scales of reality are intimately connected. The fact that quantum mechanics played a crucial role in shaping cosmic structure reveals deep connections between different branches of physics and different scales of existence. As your breathing becomes deeper and more peaceful, marvel at this profound connection between the microscopic quantum realm and the vast cosmic web that surrounds us. Cosmic dust grains act as tiny seeds from which stars and planets slowly grow. Throughout interstellar space drift, microscopic particles of dust, composed of elements like carbon, silicon, oxygen, and iron, that were created in the nuclear furnaces of ancient stars. Though each grain is incredibly small, much finer than household dust, these cosmic particles play essential roles in the universe's ongoing story of creation. Within cold, dense clouds of gas and dust, these tiny grains provide surfaces where atoms and molecules can stick together. facilitating chemical reactions that would be impossible in empty space. The dust also helps cool these stellar nurseries by absorbing heat and radiating it away, allowing gas clouds to collapse under their own gravity and form new stars. Around young stars, dust grains collide and stick together, gradually building up larger and larger objects that eventually become asteroids, comets, and planets. Even the complex organic molecules that serve as the building blocks of life often form on the surfaces of these cosmic dust grains. As you rest peacefully, think of these tiny architects of creation, working patiently throughout space to build new worlds from the ashes of old stars. Light years provide a convenient way to measure the vast distances between stars and galaxies. When we talk about cosmic distances, ordinary units like miles or kilometers quickly become unwieldy. A light year, the distance light travels in 1 year, equals about 6 trillion miles, giving us a more manageable way to express cosmic scales. The nearest star beyond our Sun, Proxima Centauri, lies about 4 light years away, meaning its light takes 4 years to reach Earth. When you look at this star, you're seeing it as it appeared 4 years ago. The center of our Milky Way galaxy is about 26,000 light years from Earth, while our nearest major galactic neighbor, Andromeda, is roughly 2.5 million light years distant. The most remote galaxies we can observe are over 13 billion light years away, showing us what the universe looked like when it was very young. Using light years helps us appreciate both the immense scale of the cosmos and the intimate connection between space and time that governs everything we observe. As you feel your body settling deeper into relaxation, imagine light from distant stars beginning its long journey years ago, traveling across space to reach your eyes at this very moment. The oldest light in the universe carries a temperature just a few degrees above absolute zero. The cosmic microwave background radiation that fills all of space represents the cooled remnant of the hot, dense conditions that existed in the early universe. Over nearly 14 billion years of cosmic expansion, this ancient light has been stretched and cooled until it now has a temperature of only about 2.7 degrees above absolute zero, the coldest possible temperature in the universe. This frigid glow surrounds us everywhere, a constant reminder of the universe's fiery beginning and its long journey toward cooler, more expanded conditions. The near-uniform temperature of this background radiation carries tiny variations that seeded all the cosmic structures we see today. Despite being incredibly cold, this ancient light connects us directly to the universe's birth and provides crucial information about cosmic history, composition, and evolution. As your breathing becomes more peaceful and regular, imagine being gently bathed in this primordial cold light that has traveled across space and time since the universe's infancy. Cosmic ray showers constantly cascade through Earth's atmosphere like invisible rain. Every second, high-energy particles from space, cosmic rays, traveling at nearly the speed of light, collide with atoms in Earth's upper atmosphere. These collisions create cascades of secondary particles that shower down through the atmosphere, with some reaching Earth's surface. Millions of these invisible cosmic ray particles pass through your body every day without you noticing. Scientists study these particle showers using networks of detectors around the world, learning about the most energetic processes in the universe from the cosmic rays that reach us. These high-energy messengers connect us to violent events like supernova explosions, black hole jets, and other extreme phenomena happening throughout the galaxy and beyond. Cosmic ray showers also influence atmospheric chemistry and may play subtle roles in climate and weather patterns. As you continue to relax, think of this constant, gentle rain of cosmic particles connecting Earth to the energetic processes unfolding across the universe. Vast cosmic voids influence how galaxies move and cluster around their empty borders. The enormous empty regions called cosmic voids don't just passively exist between galaxy clusters, they actively influence the motion and evolution of matter in their vicinity. The low density of matter within voids creates gravitational effects that push surrounding galaxies outward, toward the denser regions where galaxy clusters form. This outflow from voids helps maintain the cosmic web structure and affects how galaxies cluster along filaments. Voids also expand faster than the average cosmic expansion rate, growing larger over time and becoming even emptier. Understanding void dynamics helps scientists study dark energy, since these regions are dominated by the mysterious force that drives cosmic acceleration. The existence and properties of cosmic voids provide important constraints on theories about dark matter, dark energy, and the overall evolution of cosmic structure. As you feel your muscles relaxing completely, imagine floating peacefully within one of these vast empty regions, surrounded by the profound stillness of nearly empty space. Jets from supermassive black holes can sculpt and reshape entire galaxies over millions of years. When supermassive black holes at the centers of galaxies actively consume surrounding matter, they often launch powerful jets of charged particles that extend far beyond their host galaxies. These jets, traveling at nearly the speed of light, can stretch across millions of light years and profoundly affect their galactic environments. By heating and dispersing gas clouds, black hole jets can shut down star formation in their host galaxies or trigger new bursts of stellar birth in regions where they compress interstellar material. Over millions of years, these jets act like cosmic sculptors, carving cavities in the hot gas that surrounds galaxy clusters and regulating the growth and evolution of the largest structures in the universe. The feedback between supermassive black holes and their host galaxies represents one of the most important processes shaping cosmic evolution. As you rest more deeply, picture these cosmic jets as gentle streams of energy flowing through space, connecting black holes to their galactic communities across vast distances. The era called Cosmic Dawn marked the end of the universe's dark childhood. For hundreds of millions of years after the cosmic microwave background was released, the universe remained a cold, dark place with no sources of light to illuminate the cosmic night. This period, known as the Cosmic Dark Ages, ended when the first stars began to shine in the hearts of primordial galaxies. The epoch of Cosmic Dawn represents the universe's transition from darkness to light, when the first stellar fires ignited and began transforming the cosmos. These early stars and galaxies not only provided the first illumination since the Big Bang, but also began the processes that would clear the cosmic fog and create the transparent universe we observe today. Cosmic Dawn marked the beginning of the universe's transformation from a simple, dark void into the complex, light-filled cosmos teeming with stars, planets, and possibilities. As your body grows more peaceful and still, imagine that first cosmic sunrise when starlight began to shine across the universe for the very first time. The universe's oldest light fills every corner of space with an almost perfectly uniform glow. No matter where you travel in the universe, you would be surrounded by the gentle glow of the cosmic microwave. Background radiation, ancient light that has been journeying through space for nearly 14 billion years. This primordial radiation fills the entire cosmos with remarkable uniformity, varying in temperature by only tiny amounts from place to place. The near-perfect smoothness of this background light reflects the conditions that existed in the early universe before gravity had time to amplify small density differences into the large-scale structures we see today. This ancient glow represents the universe's transition from an opaque to transparent state and provides our most direct observational connection to cosmic history. The cosmic microwave background serves as a constant reminder that we live within a universe with a definite beginning and a rich evolutionary history. As you sink deeper into relaxation, feel yourself gently embraced by this ancient light that connects you to the universe's fiery birth and the long journey that brought us to this moment. Scientists chart cosmic history by measuring the ages of galaxies at different distances. When astronomers observe galaxies billions of light years away, they're looking back in time to see these stellar systems as they existed in the distant past. By analyzing the light from galaxies at various distances, scientists can determine when different galactic populations formed their stars and estimate how old these systems are. The most distant galaxies appear to us as they were when the universe was very young, providing snapshots of cosmic evolution across many different epochs. This technique of cosmic archaeology allows researchers to trace how star formation rates, galaxy sizes, and chemical composition have changed over billions of years. Combined with theoretical models and other observations, studying galaxy ages at different distances reveals the detailed story of how matter evolved from the simple, hot conditions after the Big Bang into the rich variety of cosmic structures we observe today. As your mind grows quieter and more peaceful, think of astronomers as cosmic historians, reading the universe's autobiography written in the ancient light of distant stars. The ongoing process of cosmic evolution describes how everything changes across billions of years. Cosmic evolution encompasses the grand transformation of the universe from its hot, dense beginning to its current state, and includes the formation and evolution of stars, galaxies, planets, and all the structures we observe. This cosmic story unfolds across an enormous range of scales, from the quantum fluctuations that seeded cosmic structure to the largest galaxy superclusters that span hundreds of millions of light years. Over billions of years, gravity has assembled matter into increasingly complex arrangements. While stellar nucleosynthesis has enriched the universe with heavy elements, and cosmic expansion has carried structures to ever greater separations. Understanding cosmic evolution reveals the deep connections between physics, astronomy, and even biology, showing how the same fundamental processes that shape galaxies and stars also created the elements and conditions necessary for planets and life. As you feel your breathing becoming slower and deeper, contemplate your place within this vast cosmic story, where every atom in your body connects you to the universe's long history of creation and transformation. Cosmic variance serves as a humble reminder of the limits of our cosmic knowledge. Because we can observe only a single universe, our own astronomical measurements necessarily carry fundamental uncertainties that cannot be eliminated by building better instruments or conducting more observations. This limitation, called cosmic variance, arises from the fact that we have no other universes to compare with our observations. When scientists measure things like the distribution of galaxies or fluctuations in the cosmic background radiation, they must account for the possibility that some features might be unique quirks of our particular cosmic realization rather than universal truths. This uncertainty challenges researchers to develop sophisticated statistical methods and theoretical frameworks to separate genuine cosmic principles from potential cosmic accidents. Cosmic variance reminds us that our perspective on the universe, however vast it may seem, is necessarily limited and unique. As you continue to rest peacefully, appreciate the remarkable fact that all human knowledge about the cosmos comes from careful study of this single, precious example of a universe that we call home. The complex interaction between cosmic rays and solar wind affects space weather around Earth. Cosmic rays from deep space encounter the solar wind, a stream of charged particles flowing outward from our sun, creating a complex interaction that influences how many high-energy particles reach Earth's vicinity. When solar activity increases, the enhanced solar wind can partially deflect cosmic rays, reducing the number that penetrate to Earth's atmosphere. Conversely, during periods of low solar activity, more cosmic rays can reach our planet, affecting ionization levels in the upper atmosphere and potentially influencing cloud formation and climate. This interplay between cosmic rays and solar wind creates a form of space weather that can affect satellite operations, astronaut safety, and even Earth's atmospheric chemistry. Understanding this relationship helps scientists predict and prepare for space weather events that might impact technology and human activities. As you feel your body relaxing more completely, think about how Earth exists within this dynamic cosmic environment, constantly interacting with both our local star and energetic particles from the distant galaxy. Magnetic fields spanning entire galaxies help shape cosmic evolution across vast scales. Though invisible to our eyes, magnetic fields thread through galaxies on scales of thousands of light-years, influencing the motion of charged particles and the behavior of interstellar gas. These galactic magnetic fields play crucial roles in regulating star formation by affecting how gas clouds collapse and fragment. They also guide the propagation of cosmic rays through galactic space and influence how matter falls into central supermassive black holes. Despite being much weaker than Earth's magnetic field, galactic magnetic fields have enormous influence due to their vast extent and their interaction with the ionized gas that fills interstellar space. Understanding these magnetic forces helps astronomers explain how galaxies maintain their structure, regulate their star formation, and interact with their cosmic environments over billions of years. As your mind grows more peaceful and quiet, imagine these invisible magnetic threads weaving through space, creating hidden connections between distant parts of galaxies and adding another layer of complexity to the cosmic web that the epoch of reionization made the universe transparent to ultraviolet light for the first time. During the universe's infancy, neutral hydrogen gas filled space and absorbed most ultraviolet light, keeping the cosmos opaque and dark. When the first stars and galaxies began shining with intense ultraviolet radiation, they gradually ionized this hydrogen gas, stripping electrons from atoms and transforming the neutral gas into a transparent plasma. This epoch of reionization represents one of the most important phase transitions in cosmic history, fundamentally changing the universe's optical properties and enabling light to travel freely across vast distances. The reionization process was patchy and gradual, with bubbles of ionized gas slowly expanding around early galaxies until they merged and filled most of space. This cosmic clearing of the hydrogen fog opened ultraviolet windows throughout the universe and set the stage for the formation of the complex cosmic structures we observe today. As your breathing becomes even more peaceful and regular, picture this gradual cosmic awakening when starlight first began to clear the primordial fog that filled the early universe. The cosmic dawn era ended the universe's dark and mysterious childhood forever. Before cosmic dawn, the universe was a cold, dark expanse filled with neutral gas that absorbed most light, creating a cosmic dark age that lasted for hundreds of millions of years. The formation of the first stars and galaxies marked the end of this dark epoch and the beginning of the universe's luminous phase. These early stellar communities not only provided the first sources of light since the cosmic microwave background, but also began the chemical processes that would enrich space with heavy elements, and the energetic processes that would clear the cosmic fog. Cosmic dawn represents the universe's transition from simplicity to complexity, from darkness to light, and from stagnation to active evolution. This epochal change set in motion all the processes that would eventually lead to the rich cosmic ecosystem of galaxies, stars, and planets that surrounds us today. As you rest more deeply, imagine this cosmic sunrise when the universe awakened from its long dark sleep and began its journey toward the star-filled cosmos we inhabit. Cosmic strings, if they exist, could reveal the deepest secrets of fundamental physics. Theoretical physics predicts the possible existence of cosmic strings, incredibly thin, one-dimensional defects in space-time that might have formed during phase transitions in the very early universe. These hypothetical objects would be thinner than atomic nuclei, but could stretch across the entire observable universe, containing enormous amounts of energy concentrated in virtually no volume. If cosmic strings exist, they could produce detectable gravitational waves as they oscillate and interact, or create subtle but characteristic distortions in the cosmic microwave background radiation. Their discovery would provide unprecedented insights into the physics of the early universe, the fundamental forces of nature, and the structure of space-time itself. Cosmic strings represent a fascinating link between the quantum world and cosmology, potentially offering clues about how the fundamental forces separated during the universe's birth. As you feel your body settling into complete relaxation, imagine these invisible cosmic threads that might weave through the fabric of reality, carrying secrets about the deepest levels of physical law. The theory of cosmic inflation elegantly explains the universe's remarkable uniformity and structure. Cosmic inflation proposes that during an incredibly brief period in the universe's first fraction of a second, space itself expanded exponentially, growing faster than the speed of light. This rapid expansion would have smoothed out any irregularities in the early universe, explaining why the cosmos appears so uniform on large scales today. At the same time, inflation would have stretched tiny quantum fluctuations to cosmic sizes, creating the seeds that eventually grew into galaxies and large-scale structures. Inflation theory solves several puzzles about the universe's properties, including why space appears geometrically flat and why regions of the cosmic microwave background that could never have communicated still have nearly identical temperatures. This elegant theory links quantum mechanics to cosmology and provides a framework for understanding both the universe's large-scale uniformity and its small-scale structure. As your mind grows more peaceful and still, contemplate this remarkable idea that the vast cosmos we observe today grew from something smaller than an atom in less time than light takes to cross a proton. Ancient photons from the Big Bang continue, carrying messages about the universe's origin. The photons that make up the cosmic microwave background radiation have been traveling through space for nearly 14 billion years, carrying with them encoded information about the conditions that existed when they were first released. These ancient particles of light have witnessed the entire history of cosmic evolution, from the universe's transition to transparency through the formation of the first stars and galaxies to the present day. By studying these primordial photons with ever more sensitive instruments, scientists can decode messages about the universe's composition, age, and evolution that are written in their properties. These cosmic messengers provide our most direct connection to the universe's birth and the processes that shaped its early development. Every measurement of the cosmic microwave background reveals new details about cosmic history and tests our theories about fundamental physics. As you continue to rest peacefully, think of these patient photons that have journeyed across space and time to bring us news from the universe's infancy. The discovery of cosmic rays over a century ago opened new windows on the universe. In the early 1900s, scientists noticed mysterious radiation that seemed to come from outer space, eventually identifying these signals as high-energy particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. Early experiments by pioneers like Victor Hess, who carried radiation detectors in balloons high into the atmosphere, proved that this radiation became stronger at higher altitudes, confirming its extraterrestrial origin. This discovery marked the birth of cosmic ray physics and provided the first evidence that space is filled with energetic particles from violent astronomical events. Over the past century, cosmic ray research has revealed fundamental particles, provided insights into stellar explosions and black hole jets, and connected Earth to the most energetic processes occurring throughout the galaxy. The study of cosmic rays continues to provide unique information about extreme physics and cosmic acceleration mechanisms that cannot be studied in any other way. As your breathing becomes deeper and more regular, appreciate how this century-old discovery continues to link us to the most powerful events happening across the cosmos. Cosmic horizons represent the fundamental limits of human observation and knowledge. Because the universe has a finite age of about 13.8 billion years, light from beyond certain distances simply hasn't had enough time to reach us since the Big Bang. This creates a natural boundary called the cosmic horizon that defines the limits of the observable universe. Beyond this horizon may lie countless more galaxies, stars, and perhaps even other forms of life. But they remain forever beyond our ability to observe due to the fundamental constraint imposed by the finite speed of light and the finite age of the universe. As the universe continues to age, the cosmic horizon gradually expands, slowly revealing more distant regions of space. However, due to the accelerating expansion driven by dark energy, some regions that are currently beyond our horizon may remain forever unreachable. These cosmic boundaries remind us that our knowledge of the universe, however vast, is necessarily limited by the fundamental properties of space, time, and light. As you feel your body growing more peaceful and still, contemplate these cosmic horizons that separate the known from the unknowable, inspiring both humility and wonder about the vastness that lies beyond our sight. The cosmic microwave background provides our oldest snapshot of the universe's infancy, when the cosmic microwave background radiation was released about 380,000 years after the Big Bang. It captured a detailed image of what the universe looked like at that crucial moment when it first became transparent to light. This ancient radiation serves as our oldest baby picture of the cosmos, showing us the tiny temperature and density fluctuations that would eventually grow into the largest structures in the universe. The near-perfect uniformity of this background light reveals that the early universe was remarkably smooth, with variations of only a few parts per million that provided the gravitational seeds for future cosmic evolution. Modern measurements of the cosmic microwave background have confirmed many predictions of Big Bang cosmology and provided precise values for fundamental cosmic parameters like the universe's age, composition, and geometry. This primordial glow continues to provide crucial tests of our theories about inflation, dark matter, and the processes that shaped the early universe. As you sink deeper into relaxation, picture this ancient light as a cosmic time capsule, carrying precious information about the universe's birth across billions of years of space and time. Subtle polarization patterns in ancient light offer clues about gravitational waves from inflation, beyond its temperature variations. The cosmic microwave background radiation also exhibits polarization, a pattern in the orientation of light waves that carries additional information about conditions in the early universe. This polarization can potentially reveal the signatures of primordial gravitational waves generated during cosmic inflation, providing direct evidence for this crucial epoch in cosmic history. The detection of these polarization signatures would offer unprecedented insights into the physics of the early universe and the processes that shaped space-time itself. During the first moments after the Big Bang, however, measuring these incredibly subtle signals requires extraordinary precision and careful separation from foreground sources of contamination. The search for primordial gravitational wave signatures in cosmic microwave background polarization represents one of the most challenging and potentially rewarding frontiers in modern cosmology. As your mind grows quieter and more peaceful, think about these delicate patterns woven into ancient light, potentially carrying messages about gravitational waves from the universe's first moments. Cosmic filaments contain much of the universe's ordinary matter in hard-to-detect forms, while galaxies and stars represent the most visible components of the cosmic web. Most of the universe's ordinary matter actually exists in the vast filaments that connect galaxy clusters across hundreds of millions of light years. This matter exists primarily as hot, diffuse gas that emits very little light, making it challenging to observe directly. However, this intergalactic medium plays crucial roles in cosmic evolution, providing reservoirs of material for galaxy formation and channels for matter transport across cosmic scales. Scientists study this hidden matter through its absorption of light from distant quasars and its subtle gravitational effects on the cosmic microwave background. Understanding the distribution and properties of matter in cosmic filaments helps reveal how galaxies acquire their gas supplies and how chemical elements are distributed throughout the universe. As you continue to rest peacefully, imagine these invisible highways of matter stretching across the cosmos, carrying the raw materials for star and galaxy formation along the hidden scaffolding of the cosmic web. Powerful jets from supermassive black holes can extend for millions of light years. Some of the most spectacular phenomena in the universe are the enormous jets of charged particles that supermassive black holes can launch from their vicinity. These jets, traveling at nearly the speed of light, can extend far beyond their host galaxies, stretching across millions of light years of intergalactic space. The jets transport enormous amounts of energy from the central black hole to distant regions, heating the surrounding gas and influencing star formation across entire galaxy clusters. By studying these cosmic jets, astronomers can learn about the physics of black hole accretion, the behavior of matter under extreme gravitational conditions, and the ways that supermassive black holes communicate with their larger cosmic environments. The longest jets observed extend farther than the distance between our Milky Way galaxy and its nearest major neighbor, demonstrating the incredible reach of these black hole-powered phenomena. As you feel your body becoming completely relaxed, picture these cosmic jets as streams of energy flowing through space, connecting the hearts of galaxies to the vast cosmic web that surrounds them. The legacy of cosmic inflation remains encoded in the subtle patterns of ancient light. During the brief epoch of cosmic inflation that occurred in the universe's first fraction of a second, space expanded exponentially and stretched tiny quantum fluctuations to macroscopic scales. These fluctuations became the seeds of all cosmic structures, galaxies, clusters, and the cosmic web. All trace their origins back to quantum ripples that inflation amplified to cosmic proportions. The imprint of inflation remains visible today in the delicate patterns of temperature and polarization variations observed in the cosmic microwave background radiation. By studying these subtle signatures with ever more sensitive instruments, scientists can probe the physics of the early universe and test theories about fundamental forces and particles. The detection of inflation's legacy in ancient light provides one of our most direct connections to the quantum processes that shaped the cosmos and reveals the profound unity between the smallest and largest scales of reality. As your breathing becomes slower and deeper, marvel at how the vast structures of the modern universe grew from quantum seeds planted during inflation's brief but crucial reign. Cosmic rays may subtly influence Earth's climate through their effects on cloud formation. Some scientists have proposed that cosmic rays, high-energy particles from space that constantly bombard Earth's atmosphere, might affect our planet's climate by influencing cloud formation. When cosmic rays collide with molecules in the atmosphere, they create ions that could potentially serve as condensation nuclei for water droplets, affecting how clouds form and evolve. Changes in cosmic ray intensity, caused by variations in solar activity or our solar system's motion through the galaxy, might therefore influence cloud cover and Earth's energy balance. While this potential connection between cosmic phenomena and terrestrial climate remains a subject of ongoing research and debate, it represents a fascinating example of how Earth exists within a dynamic cosmic environment where distant astrophysical processes might subtly influence local conditions. This possible cosmic climate connection reminds us that our planet is not isolated from the broader universe, but constantly interacts with cosmic forces in ways we're still discovering. As you rest more deeply, think about these subtle connections between the cosmos and Earth's atmosphere, linking distant stellar explosions to the clouds that drift across our sky. Galactic movements follow the invisible highways carved by cosmic filaments. Galaxies don't move randomly through space, but follow preferred paths determined by the large-scale distribution of matter, especially the invisible dark matter that dominates cosmic mass. These gravitational currents guide galaxies along the filaments of the cosmic web, channeling them toward dense clusters and away from nearly empty voids. Our own local group of galaxies, including the Milky Way and Andromeda, participates in these large-scale flows as we're gradually pulled toward massive concentrations of matter, like the Virgo cluster. Understanding these cosmic currents helps astronomers map the invisible architecture of dark matter and predict how cosmic structures will evolve over time. The motion of galaxies along these predetermined paths reveals the fundamental role that invisible matter plays in shaping the observable universe and guiding the cosmic dance that has been unfolding for billions of years. As you feel your muscles relaxing completely, picture these invisible currents flowing through space, gently guiding galaxies along cosmic highways that stretch across hundreds of millions of light years. Neutrinos offer unique windows into the puppet universe's most violent and energetic processes. These ghostly particles, which barely interact with matter and can pass through entire planets unimpeded, are produced in some of the universe's most extreme environments. Neutrinos stream from the nuclear fires of stars, burst forth from supernova explosions, and emerge from the vicinity of actively feeding black holes. Because neutrinos interact so weakly with matter, they can escape from regions where light cannot, carrying direct information about processes occurring deep within stellar core or near black hole event horizons. Detecting these elusive messengers requires enormous, sensitive instruments built deep underground or under thick ice to shield them from other particles. Each neutrino detection provides precious information about fundamental physics and astrophysical processes that would otherwise remain hidden from observation. As your mind grows more peaceful and quiet, think of these invisible messengers streaming through space and through your body right now, carrying news from the universe's most energetic and mysterious phenomena.